right, here we are moving into section 4.5, where we are now going to use the idea of our derivatives in the sense of maximum and minimum to solve some application problems, some real world problems that you may have. So the theme of this section is optimization. It's a topic arising in many disciplines that rely on mathematics. A structural engineer may seek the dimensions of a beam that maximizes the strength for a specific cost. A packaging designer may seek the dimensions of a container that maximizes the volume of the container for a given surface area. Excuse me there, a little typo. And then airline strategists need to find the best allocation of airliners among several hubs to minimize fuel costs and maximize passenger miles. So if you see that maximize and minimize, that's where a lot of this comes into play when we talk about optimization problems. In all these examples, the challenge is to find an efficient way to carry out a task. So here's some guidelines for optimization problems. And these are just some things, step-by-step process for you to work through when answering some of these problems. Will you do every single step all the time? Maybe not, but will you do most of them? Absolutely. Now, number one, the first thing is to read the problem carefully. For any word problem, read that problem carefully, identify the variables, and organize the given information with a picture, if it can be. Now, number two is really, really important because we want to identify the objective function. What is it that we are being optimized? What are we maximizing? What are we minimizing? And we want to write that in terms of variables of the problem. And that could be in terms of two different variables. But in number three, what we want to identify are any constraints. A constraint is going to be an equation of some other information that we know that would be allowing us to take some of those two variables in step two and change it just into one variable. And then we are going, that would be number four, use the constraints to eliminate all but one independent variable in the objective function. Then we're going to write that objective function in a single variable by doing a little substitution. Find the interval of interest for that variable, and then we're going to use methods of calculus to find the minimum or maximum, aka find the first derivative of that objective function to find the answer. So let's look at this first problem here. What two non-negative real numbers with a sum of 36 have the largest possible product? The largest, a maximum possible product. So basically I have two numbers. I'm going to call one of them x and the other one y. Okay, those are my two numbers. Now, the first part there says that I have a sum of 36. I'm going to add those two to equal 36, and this is what we refer to as one of those constraint equations, that x plus y equals 36, because our objective function is what we want to maximize. So I'm going to use P for product, and the product of my two numbers is xy. So this is my objective function right here. Problem is you don't want to take the derivative of that. You'd have to do some implicit differentiation and such and do some y primes. You don't want to do that. We want to take our constraint and solve that for one or the other. Doesn't matter. Normally we like to go in terms of x. And then we're going to sub that back in. So if I ask you what is the equation here in terms of x, that would mean I have to solve it for y. I would have to subtract the x over, and I get y is equal to 36 minus x. And that is what I want to do now in step 4 to substitute that in. So I kind of went, I think I wrote my constraint function first before my objective function. So I kind of went out of order, but you want to make sure that you have all of them. So I'm going to replace the y with what it's equal to as a 36 minus x. And now I'm going to simplify this function as 36x minus x squared. So that is a nice polynomial function. That is a negative x squared, means I have a parabola that is going upside down, which means that I would, yes, have a maximum value. So we're going to figure out where that max is. Well, from our work in earlier of chapter 4, the maximum occurs at one of those critical points. And a critical point happens whenever I take the derivative of this function, call it p prime. I'm going to take the derivative here, which is 36 minus power rule gives me a 2x. And now I have to set that equal to 0. It's not going to be undefined anywhere. It's going to be equal to 0 to kick out a critical number. And when I do that, I get 36 equals 2x when I add over 2x. And when I divide by 2, I get x to equal 18. Now, we haven't talked about the interval of interest. Here, I have two numbers that add to equal 36. Well, I can, for any non-negative real numbers, non-negative would start at 0, but what is the matching number that could be when I add those together to equal 36? Well, that would be 36. So my interval of interest here is from 0 to 36. Now, going back to the idea of absolute value, or sorry, absolute max and min, we had a theorem that said if I had a smooth continuous function, then over a certain interval, there is guaranteed to be an absolute max and an absolute min. Here, we're just worried about the maximum for the largest. But what we had to do was we had to evaluate our endpoints, and we had to evaluate any critical numbers to determine which actually yields the highest value. So this is what we have to do in our final answer, is to figure out which one of these gets the highest. So actually I probably shouldn't put F there, I should probably put P. But when I plug that into the original function, I get a 0. If I plug 36 into this original function, because of right here with these factors, that's going to give me 0. And when I throw 18 into that function, 18 times 18 actually, that would be 324. Therefore, the two non-negative numbers that I have is going to yield me the x to equal 18. I can plug that back in and find the y value. So the y value is 36 minus 18, which is also 18. And the maximum product is what we get when we evaluate that function at that critical point. Okay, so let's make sure we answer the question. What two non-negative real numbers with a sum of 36 have the highest or the largest possible product? The two numbers are 18 and 18. If I would say what is the actual product, then the actual product, that answer would be 324. So make sure you go back and you figure out what is the question that they are asking. Okay, so that's one of those types of problems. Let's look at this next one. It says, of all rectangles of area 200, which one has the minimum perimeter? So what are we maximizing or minimizing? We're minimizing the perimeter here. This is the objective function that we need to write. But there is a constraint for us. This is the constraint, that we have an area of 200. This is going to help us create this function in terms of just one variable. So we're talking about a rectangle, so I'm going to draw a rectangle, and I'm going to apply some values to there. Just call them x and y. You can call them L and W for length and width. It doesn't matter. But we need to write the objective function first, and then the constraint, or vice versa. Then we're going to plug one into the other. So let's just start with the perimeter. If I want to minimize the perimeter of a rectangle given a length of x and a width of y, I need two x's and two y's to give me the perimeter. So that's my function that I need to maximize or minimize in this case. The constraint comes from this piece of information that says the area of this rectangle is 200. So to find the area of a rectangle, I have to do xy equals 200, and that is my constraint equation that I'm going to use to get my perimeter function in terms of one letter. Again, a lot of times we like to do it in terms of x. So let's solve for y. If I do that, that means I'm going to divide by x. So y is equal to 200 divided by x. That now is what we want to plug in step 4 to get our function in terms of one letter. So we get 2x plus 2 times 200 over x. Now, what is that equivalent to? That is equivalent to 2x plus 400 over x. And in order for me to be able to take the derivative of that, I'm going to rewrite this function now as p is 2x plus 400 times x to the minus 1. I'm going to bring this letter up to the top so I can use a power rule on it. All right, very good. So let's now take a derivative. the derivative here of this function is that I'm going to end up having 2, and then bring the negative out front, gives me a negative 400 x to the minus 2. Now, we need to simplify that so that I can now find a critical point. I'm going to write that as 400 over x squared. And getting a common denominator means I'm going to multiply by x squared here. This gives me 2x squared minus 400 all over x squared. So this is where we need to determine our critical numbers. Now, if I am looking at what is the interval of interest that I have, then I need to determine from my constraint function or from my perimeter function what is kind of some allowable values that I have there. And so, since our xy equaling 200 has to be greater than 0, then that shows that from here, when I solve for y, that if x is greater than 0, this whole thing's going to be greater than 0. So the interval of interest that we're looking at here is for, it's kind of an infinite one, from 0 to infinity for this situation, okay, for the x values. All right, so now we need to look at what is our critical number, first off, and then what is going to minimize that using our endpoints that we have. But since we have an open interval here from 0 to infinity, there's really no closed interval that we have when working with an absolute value and absolute min. So technically, we're just going to be checking this critical number. Now, if I let x equal 0 here, that's an undefined piece. Well, that doesn't make sense if I have x times 0 times something. That's never going to give me an area of 200. So x can't equal 0. What I really want to look at is this 2x squared minus 400. So, if I let 2x squared minus 400, where is that equal to 0? I now can figure that out. Now, here you can divide by 2 if you want, then you can do a difference of squares, but I'm going to solve this by adding 400 over to get 2x squared equals 400. Dividing by 2 says that x squared is 200, and then when I square root both sides, now normally there's a plus or minus on this side, but x is a length here. X can't be negative, so I'm going to choose x to be, this is 100 times 2. We can reduce that to be 10 root 2 as the x value. So the x value is 10 root 2. That's part of the dimensions. Which one has a minimum? We need to know what the dimensions are. That's part of it. But I need to now plug that back in over here to figure out what y is equal to. So if I do y equals 200 over 10 root 2, I'm going to first cancel the 10 into 200 and give me, a 20. So I get 20 over root 2. I have it different on my paper, sorry. And so then I rationalize this to multiply by 2, root 2, multiply by root 2. And this piece right here is actually 2 that I would cancel into 20 and give me a 10. So this actually turns out not only to be a rectangle, but actually a square as well. So this is a 10 root 2 by 10 root 2 rectangle that would minimize the perimeter when we have an area of 200. Okay? All right, very good. So now let's evolve into another type of problem, another application dealing with perimeter and area. So here we have a rancher has 400 feet of fencing for constructing a regular corral. One side of the corral will be formed by a barn and requires no fencing, and that is this side that we see right here. No fence required. 3 exterior fences and 2 interior fences partition the corral into 3 rectangular regions as shown in this picture. What are the dimensions of the corral that maximize the enclosed area, and what is the area of that corral? So we're looking for the x and the y that allows us to maximize this corral here, okay? So then it asks me for a final question of what is the actual area, okay? So we are going to end up if we're maximizing the area, then our objective function has to come from the area of this rectangle. Well, we just talked about area up here. It is length times width, so we're going to let x times y be our objective function. Now, the constraint this time, it's kind of reverse of what we were doing up here. We were minimizing perimeter given the constraint of area. Now we are maximizing the area given a constraint of perimeter. It says that we have 400 feet for fence. And I have a fence here, a fence here, a fence here, a fence here. So I have 4 x's and 1 y that I have to use that 400 feet. So that means that 4x plus y has to equal 400. We don't have anything along this way. Okay, now to figure out what our constraint is, obviously we're going to solve that for y to plug in here. So when I subtract 4x, then y equals 400 minus 4x. Now, to find our interval of interest, it's kind of nice when we're dealing with perimeter stuff, because what we can actually do is just figure out what makes this equal to 0. Because if I start where x is nothing and I have all of y, then what is the max that y could be? Well, if I put if I set this equal to 0 to find out what the y is, you can add over 4x and divide by 4. So our interval of interest here is actually from 0 to 100. So again, when you're working with area and the constraint is a perimeter, it's different when your constraint is area. Here, you can figure out where that's going to be equal to 0, and that'll help you out with your interval of interest, okay? So that's our interval of interest. It is on a polynomial function it'll end up being a polynomial function once I add this in here. So I'm going to change this as to x times 400 minus 4x. There's my polynomial function. That, given it to be continuous on a closed interval, then we would have an absolute max or an absolute min. We don't care about the mins this time. All we want to know is what is the max in this case. So I'm going to distribute my x through. And my final objective function before I take a derivative looks like this, 400x minus 4x squared. So now let's take our derivative to maximize this area function. When I do that, I'm going to get 400 minus 8x. And in order to determine where the max occurs, I'm going to have to set this equal to 0 to find a critical point. So I get 400 equals 8x when I add over the 8x. And when I divide by 8, I end up with x equaling 50. So that x equaling 50, that is the possibility for my maximum area here. So in order to solidify that, I have to determine with my endpoints at 0 and 100, and consider that 50 as my critical point, and determine what is the maximum area. So I'm going to go back to that original function right here in terms of x. If I throw 0 into here, 0 times whatever that is going to be 0. If I put 100 in here, and this is going to help me with my constraint. Remember, we figured out where that was equal to 0 to help us out. If I put 0 in here, that's going to give me 0 times 100 is still 0. And when I throw 50 in here, 50 times 400 minus 4 times 50, well, that's 200. So we get 200 times 50 is actually going to be 10,000. And that gives us the biggest number. So if we evaluate all these numbers, this is my max, these are my mins. We don't care about the mins, we just care about the max. So to answer the question, we want to know what are the dimensions of the corral. So we need to know the x times the y. So the x equaling 50 is one of those dimensions. But now y equaling 400 minus, 4 times 50 gives me my other dimension. And so 400 minus 200 is going to be a 200 as well. So the corral's dimension is a 50 feet by 200 feet corral. And that's the first question. The second question says, what is the area of that corral? And the area is this right here. So the area is equal to 10,000 square feet. And that's going to be our final answer there. Okay? All right, very good. So I know sometimes word problems are a little bit harder, but if you will, just kind of break them apart and help you out to find those maxes and those mins. All right, I want to change up the color a little bit. Let's go to blue. We have a rectangle this time that is constructed with its base on the diameter of a semicircle that has a radius of 3 and its 2 other vertices on the semicircle. What are the dimensions of the rectangle with a maximum area? Again, we're maximizing area of a rectangle. So I'm going to say area is equal to x times y again. That's going to be our formula. But we need to determine kind of our constraints as well. And that constraint is dealing that I am inside a semicircle of radius 3. So that's -3, that's +3, and a +3. I have a rectangle that is sitting inside of that, whose one length is, and I'm not very symmetric here, so I apologize. This should be the same as that. And I'm going to call this distance x, which would make from 0 to here -x, okay? So this side of the rectangle lies on the diameter of the semicircle, and the other 2 vertices are on the semicircle. That's what we're describing up there. Now, you have to remember that this from here to here is x, but this is -x, so the whole distance that I have here, I have an x and an x, leaves me with a 2x. Now I'm going to let that be y, okay? So actually, my area function, I need to throw in a 2 here, because I'm going to take 2x times y the way I've set it up. Now, you can actually make this just x, that whole distance, but the problem is here, excuse me, is that this would have to be an x over 2, not just an x. So in math, we have our own ability to make things nice for us, okay? I'm not going to have that fraction. I'm going to use just a whole number here for that. All right, now the other constraint that we have to worry about is what is this distance of y? I need to take that out and keep it in terms of just x. Now this is going to be dependent upon the equation of a semicircle, which is not one that we've done per se quite often in Calc 1, but it is something that you should know. And so I'm going to end up reminding you that the y equal to the square root of your radius squared minus x squared is the equation of a semicircle given a value of x. So for our situation, we have a radius of 3. So if I were to plot any of these points along this semicircle for any x value that I have here, it would be on the equation of the radius squared, which is 9, minus x squared. And that is the thing I wanted to make sure to remind you of, because that we don't normally use a lot. Okay? All right, very good. Now that we have that, that's the piece that I need to put in my objective function so that I can then take the derivative. So the area here, I'm going to write 2x times the square root of 9 minus x squared. Which actually, yeah, let's go ahead and just rewrite it. Let's go 2x times the quantity of 9 minus x squared to the 1/2. So this derivative is not going to be very pretty, but we can do it using a product rule, because I have a times right there, and a chain rule for this quantity squared. So let's do a prime. I'm going to take the first times the derivative of the second. So here I need to take the 1/2 out front. Keep that the same, decrease your power by 1, and chain rule derive in the inside. So I have to take the derivative of the inside, which is -2x. Add to that the second times the derivative of the first. So the derivative of that is going to be a 2. Now here comes the fun part where you're factoring things out. Now notice here that I actually have a 1/2 and a 2 that can cancel themselves out, or a 1/2 and a 2 to cancel themselves out. Now, each of them have a 2 remaining, so I'm going to take that out. And each of them have this expression of 9 minus x squared, but they have different powers. So recall, we want to take the smallest power out. So I'm going to take out 9 minus x squared to the -1/2, and now here comes what was left over. So I take away this 2, and I'm left with an x and a negative and an x. So I'm going to write that as -x squared. And I took this complete expression out front. Okay, so I took the 2, this complete expression out front, and I'm left with an x and an x and a negative to give me that. for the next one, I take out a 2 as well, but I take out this expression, but I have to make some power work that when I add it to this negative 1/2, I get a positive 1/2. So I need this expression back in, and remember, this is the tricky one. I always try to check 1. Most of the time, 1 will work. 1 plus a half, or excuse me, 1 plus a negative 1/2 does give me that 1/2. So that is the power that I need right there for that piece of information. So I'm going to simplify. Let's keep going and simplify. We get 2 times the 9 minus x squared to the minus 1/2. And I'm going to simplify here and leave me a negative 2x squared plus 9. Now, we could go ahead and write this in the bottom if we want, but we don't have to, okay? Our restraints basically here, the allowable x values has to be from 0 to 3, so this is the interval at which we are looking on. But, obviously at 0 and 3, we're going to get an area of 0. If you try to place that in there, you're going to get an area of 0. So really what we're looking at here is for this critical number. Now, this isn't going to yield anything for us. That 9 minus x squared, well, actually it will yield the 3 and the negative 3, but the negative 3 is not going to be within our interval of interest. I need to determine where this is equal to 0. That's where my critical number is going to come from. So where is minus 2x squared plus 9 equals 0? I'm going to subtract over the 9 and get minus 2x squared equals negative 9. When I divide by negative 2, then I get x squared equals a positive 9/2. Now remember, x is a distance here. It can't be negative. So I'm going to square root both sides and say that x is equal to, take the square root of 9, which is 3, over the square roots of 2. And that right there is going to be our critical point that yields our maximum area. Now, you can check what that maximum area is. It doesn't ask me for that. It just asks me for the dimensions of the max area. So if I let x equaling 3 over root 2, I'm going to get rid of this so I have some space over here. Now I can go back and find the width and the length, okay? So let's talk about the width here. The whole thing is 2x. So the width is 2x. So I take 2 times what I found over here, which is 3 over root 2. Put this over 1 if you want, go straight across. That gives me a 6 over root 2 as my width. And my length is found by putting the, where's our length? Or, excuse me, I think I got these backwards. Maybe we say this is the length and this is the width. Or I could vice versa it. The y value is what I'm looking for. So now the y value is the square root of 9 minus that quantity, 3 over root 2 that I have to square. Okay, so now we have to figure out what this is. This is equal to 9 minus, square the top gives me 9, square the bottom just gives me a half. If I put this over 1 to get a common denominator, multiply by 2, this becomes 18 halves minus 9 halves gives me another 9 halves. And that reduces square root of the top is 3, square root of the bottom. Best I can write is square root of 2. So here's my width and here's my length. Therefore, those are the dimensions of my rectangle for this situation. So I don't have a unit on it, but we could say 6 over root 2 by 3 over root 2 rectangle would maximize the area in that situation. Okay, again, I know it looks really complex, but take it in pieces. Write that objective function. How are the other two variables related with some other constraint? Then plug that in, do your derivative, find its critical point, and then answer the question, okay? All right, so our last one is going to be in our optimization section, dealing with some volume. Suppose that an airline policy states that all baggage must be box-shaped with a sum of a length, width, and a height not exceeding 64. So it can't go over 64. It can equal 64, but it can't go over. Whether the dimensions and the volume of a square-based box with the greatest volume under these conditions. The greatest volume. That's the objective function right there. That's the objective, and this piece right here is my constraint. Okay, so let's first draw a picture of our box. It's a square base box. So I have a square, let me do this. Let me undo that. Have a box of some height, but I'm going to end up having kind of a square base. So I'm going to call this x and that y. So you can bring up whatever variables that you want. But notice that it has to be a square base here because they told us that. And so this constraint equation, given these variables, means that my length and my width and my height has to at least be 64 or less for it to hold true. And how do I find the volume objective function? Well, the volume of a box, if you remember, is length times width times height. So that would be x times y, or I'm going to write it as x squared times y. Now, this restraint or constraint is what's going to help us out to get y out of there. This is 2x that I'm going to subtract over and say that y equals 64 minus 2x. Now, what is our interval of interest? Remember, in a volume and a perimeter situation, taking this, if I let this equal 0, adding over 2x, 64 minus 2x equals 0, adding over divide by 2 tells me that my x values are allowed to be between 0 and 32. That's the interval of interest, okay? Now, most often than not, I will tell you that your max and mins occur at the critical point. So don't freak out too much on the interval of interest. That's not the whole be-all, end-all of the problem. All right, I'm going to throw this in here for y. So I get b equals x squared times 64 minus 2x. I'm going to go ahead and distribute and get 64x squared minus 2x cubed. And at that point, that's my nice polynomial function that I can take the derivative of in order to maximize that volume. So I get 128x minus a 6x squared. And this is a quadratic equation that I can set equal to 0. There is some common terms here. There's just a 2 in common. Unfortunately, there's not a 6, but just a 2. And there's an x in common. So when I take 2x away from here, I'm left with 64. When I take away 2x from here, I'm left with 3x equal to 0. And that's going to kick out my critical points. Here, a critical point means that 0 would make that 0. And at 64 minus 3x, if I set that equal to 0, I get 64 equals 3x. When I divide by 3, gives me another critical point of 64 thirds. Notice that this critical point of 0 is the same as one of the values within my interval of interest. And in order to determine the exact maximum volume, then I have to plug these values into my original function. So going back to this piece right here, I have to plug in 0, 32, 64 thirds and figure out what that is. Well, if I plug 0 in there, I get back 0. If I plug 32 in here, and you can do all that work, or you could plug 32 right here, 32 times 2 is 64. 64 minus 64 is 0. 0 times anything is going to be 0 still. And so the real deal comes whenever I plug 64 thirds in. Please use your calculator to help you out, possibly as well. This one doesn't come out very nicely because 64 thirds doesn't reduce very nicely. And this gives me a volume of 9,700 and some, a little bit over that. So, twofold on the questions. What are the dimensions of that box and what's the volume? Well, the volume I've already figured out, 9709.04. And we are in inches, so that would be inches cubed. I already know that my dimensions basically is 64 thirds by what? Well, I got to plug that into here, okay? So if I go y equals 64 minus 2 times 64 thirds, this is 64 minus 128 over 3. And if you end up multiplying this by 3, Multiplying that by 3, which would give me 192 minus 128 over 3 actually gives me 64/3 as well. Okay, which makes sense because when you start working with all these maximizing problems, then you will see that a lot of the times the square will incorporate the maximum of everything. So x is 64, we had 2 x's, and y was 64/3, so we had one of those. So notice what we have here. It is a box that has all same dimensions, so we can actually not call that a rectangular prism, we could actually call that a cube. So a cube is actually going to be the most efficient, maximizing the volume and keeping within the constraints that we have of the length, width, and height have to not exceed the 64. So this is section 4-5, and this is it is a hard section for some. So please make sure that you go in steps. You write that optimization function, you write the constraint function, you plug that in, take the derivative, find the critical points, and determine the answers to your questions on those, okay? Next, we're going to move into section 4-6, and it's going to be dealing with doing a kind of a linear approximation and evolving into what we refer to as differentials, which will be very helpful not only at the end of chapter 4, but into chapter 5 as well. So until next time.